Welcome to another session of basic mathematical analysis. Last thing we have discussed about limit superior and limit inferior. Today we will discuss some problems regarding limit superior and limit inferior. Here is the problem, or you can take it as a theorem also. I am writing as a question. A bounded sequence xn is convergent if and only if its limit superior of xn is equal to limit inferior of xn. That is, a bounded sequence xn is convergent if and only if limit superior of xn equal to limit inferior of xn. How we can prove this? So first one, we want to consider a sequence xn. So suppose xn is a sequence converges to x. Now what we want to prove? We want to prove the limit superior of xn equal to limit inferior of xn. Now we know that a necessary and sufficient condition for convergence of a sequence is that it is bounded and has a unique limit point and has a unique limit point. Thus, x is a unique limit point of xn. Thus, we have assumed that xn is sequence converges to x. Thus, x is the unique limit point of xn, sequence xn. Hence, the limit inferior, and limit superior both are equal to x, because you are taking subsequences, limits, and taking its supremum and infimum. No? So it is having a unique limit point, shows that the limit superior and limit inferior are equal to x. Thus we have proved that whenever the sequence converges, the limit superior and limit inferior are equal. Now conversely, we want to assume xn be a bounded sequence such that limit superior of xn equal to limit inferior of x, and we want to prove the sequence converges. Conversely, conversely, suppose that the sequence in sequence xn be a bounded sequence, be a bounded sequence such that our condition is limit superior of xn is equal to limit inferior of xn, such that this condition holds. And suppose this value is equal to x. Now this shows that x is the unique limit point, right? This shows that x is the unique limit point of the bounded sequence xn, since limit inferior and limit superior are smallest and greatest limit point, right? Since limit inferior and limit superior are uh, smallest smallest and greatest limit points, and greatest limit points. Thus, xn is a bounded sequence with unique limit point. Thus xn is a bounded sequence with unique limit point. Thus, xn converges to x. Xn converges to x. So we have proved that whenever a bounded sequence is converges if and only if limit superior of xn equal to limit inferior of xn. Next we are having one more problem. Next question. If sequence an be a sequence such that limit of a to n minus 1 is equal to L, and limit of a to n is equal to L, then prove that limit of a n is equal to L. So here given is an is a sequence such that limit of a to n minus 1 is L and limit of a to n equal to L. Then prove the limit of an equal to L. What is asking is We got a sequence. We got a sequence here as A1, A2, A3, A4, A5, A6, A7, A8, etc. Now considering the subsequence by taking the odd terms, that is, sorry, just A3, A3, A5, A7, etc. So that sequence A2n minus 1 is going to be 2n, n equal to 1, so I should start with 1. So this sequence is A1, A3, A5, A7, etc. This sequence converges to L. Another sequence is given as A2n subsequence, right? This subsequence is A2, A4, A6, A8, etc. This sequence also converges to L. Then this implies that the sequence AN should converges to L. So this is the thing we want to prove. So let us see how to prove it. Solution. Choose any epsilon. Choose any epsilon greater than 0 since limit of a 2n minus 1 equal to L corresponding to this epsilon corresponding to this epsilon, there exists K1 belongs to N such that modulus of A2n minus 1 minus L is less than epsilon for all n such that your 2n minus 1 is greater than or equal to K1. Call this as equation 1. Now it's also given that limit of A2n is L. So since limit of A2n is equal to L corresponding to epsilon there exists K1 belongs to N such that modulus of A2n minus L is less than epsilon for all n such that your 2n is greater than or equal to this K2. Call this as equation 2. Now from 1 and 2 what follows? If we are taking maximum of K1 and K2 or we are taking any member which is greater than K1 and K2, then for that value which is greater than K1 and K2, these two inequalities holds. That means AN, see this means all the terms of the sequence. So all the terms of the sequence and I am taking AN, then modulus of an minus L should be less than epsilon for some n greater than or equal to some k3, right? So that implies the sequence converges. From 1 and 2, from 1 and 2, it follows that modulus of ak minus L is less than epsilon for all k greater than or equal to some k3. That k3 is going to be maximum of k1 comma k2. So when you're taking k3 as maximum of this, then modulus of ak minus L is less than epsilon. So in fact, take this as equation 3. In fact, if k be odd, say 2n minus 1, then equation 3 follows from equation 1, right? And if k is an even, if k is or k3, right? k3 is even, 3 follows from equation 2. Thus from 3 we see that thus from the inequality 3 we see that an converges to L. An converges to L. That is limit of an equal to L. So that's something we want to prove. So in today's class we have seen only two problems. First problem is whenever a bounded sequence is converges, the limit superior of xn equal to limit inferior of xn, and if a bounded sequence having this property limit superior of xn equal to limit inferior of xn, then that sequence converges. And second thing, we have seen that whenever you are listing your elements of the sequence as odd positions and even position terms, and that subsequences converges to a limit, then the actual sequence also converges to the same limit. So with this, I'm winding up today's session here. Thank you for your patient listening. Thank you.